The engineering kit came with a variety of different components in order to make 3 different types of robots.
This robotic system is called a self-balancing motorcycle. The board components it uses are MKR 1000, MKR motor carrier, and MKR IMU shield. It works by using a reaction wheel and movement gyro, which makes it move around and balance itself. This robotic system is called a mobile rover, which features position tracking via connected webcam and onboard sensing to avoid obstacles and movements. To make this robot function, we use MATLAB and Simulink to program. I use an Arduino Maker 1000 board that I program using MATLAB and Arduino IDE. The way it works is by processing trajectory calculations and trajectory optimizations for path planning. The drawing robot is able to draw an image on a board using a pre-processed code and also using a webcam that can be digitalized through MATLAB. This is an Arduino Maker 1000 board, which is a powerful board. It includes a LiPo charging circuit that allows it to run on batteries. It is also able to lower its power consumption to last longer. The Maker 1000 has 28 pins, which are ground, analog pins, and voltages. The voltage threshold is between 0 to 3.3 volts. We do not want to exceed 3.3 volts because it will damage the board. This is an Arduino MKR motor carrier. What this basically controls are the servo and motors. It's compatible with all boards in the MKR family. It also has 4 DC motor inputs and 2 input encoder sensors. A DC motor causes the motor shaft to rotate when current is applied. This will help move my robotic system. This is a magnetic encoder, which is a sensor that can repeat the rotation speed and spinning direction. A servo motor is an actuator that can change its angle position and angular velocity through a microcontroller. I will briefly be talking about what each task is supposed to do. First, I have to connect my robot to my PC using a USB cable. In task 1, I will be finding the limits of the marker's displacement and the limits of the amount of voltage we can use. The code is also measuring the encoder's values to see how far they displace. Once we find these limits, we can clear the hardware variables. In task 2, we measure the base from the 2 pulleys attached onto the wall. We then use a graphical user interface that will allow us to put our links from the motor to the pulley. Knowing these values will give us our position of the robot. We are then able to use a symbol plotter app that will allow us to move the robot to any direction. We are then able to get the new position of the robot. We are then able to create a function from the previous task. We also created 2 different types of functions that can convert position to counts, and vice versa. In task 3, we are moving the drawing robot to a specific position by choosing our X and Y coordinates. We then have to measure our new distances from the motor to the pulley. Once that is completed, we then convert the position to counts using a function. We are also able to move the robot in a sequence of movements. In task 4, we use the manufacturer specifications at the voltages. We then calculate the torque with the given values from the manufacturer. This will help us with creating a grid of all possible positions. We also created a torque graph for every position on the whiteboard. We then eliminate the region close to the pulley system so nothing breaks. We also choose a specific region for the drawing robot to draw. In task 5, we are loading a MathBricks logo in order to draw the image on the whiteboard. The code is calibrating the pixels chosen from the sample image. We then convert the pixels into physical distances for the drawing robot. We also change the paths to meters and reduce the segments in the graph. We are then able to run the code in order to draw the image. In task 6, we load the same image from the previous task. We then convert the image to a grayscale and also extract the pixels in order. We also break the coordinates list into continuous segments. Once that is complete, We then merge the segments together. We store the X and Y pixel limits as well. And we then are able to draw the image we use using the previous function we have been using. In task 7, we are using a webcam to have the drawing robot draw an image on the whiteboard. We preview the webcam and we put whatever photo we want to draw, and we take a snapshot of it. We use main7.m to create the function to draw the image.